Good afternoon, dear students. Can you hear me?
Yes, I hear. Good afternoon.
Good afternoon. Thank you very much for feedback. Okay, then we can start. So let's share the screen. So we finished in our last lesson. We finished chapter 4. That means the chapter position, shape, position, and displacement. Actually, we analyzed the mechanism in this chapter. And now we will deal with the synthesis. That means how can we design a mechanism for a certain task or application. So, and that means synthesis, of course. So let's start it. So mechanism design. That means synthesis. Is it okay? So the previous chapter 4, explored methods to determine the displacement of a mechanism whose link lengths are given. So it was very important. Whose link lengths are given. Now is not given, so we have to define. So then, compared to this analysis, the design of mechanism present the opposite task. So what is the opposite task? So we have to define the length of links. So that is given a desired motion, that means the desired motion is given, and a mechanism form and dimensions must be determined. That means synthesis. So synthesis is the term given to describe the process of designing a mechanism that produces a desired output motion for a given input motion. That means we define the input motion, and there is a desired output motion. The mechanism we are going to design has to deliver, taking the input motion, mechanism has to produce the output motion. So the mainly we will deal two mechanisms: slider crank mechanism and the 4-bar mechanism. There are, you can imagine, many other mechanisms for different applications, but in the frame of our lessons, we will deal with the 4-bar mechanism, and for the design of 4-bar mechanism, we will deal with slider crank mechanism and 4-bar mechanism. Or 4-bar, that means it could be different. I mean the crank rocker and double rocker and so on. So for this reason, slider crank and 4-bar mechanism are the most widely used in industry. And that's the reason why we prefer to discuss this mechanism. This chapter focuses on these two mechanisms. You may remember from our previous lessons, slider crank mechanism. This is the crank link, this is the coupler, and this is slide link here. And for the 4-bar mechanism, we have here driver and the follower here, or driven part, and the frame here, and the coupler. So, determine the dimensions of a mechanism to achieve the desired motion. This is mechanism synthesis. So, to determine the dimensions of a mechanism to achieve the desired motion means mechanism synthesis. So after selecting a mechanism type, but we should also estimate which type of mechanism is suitable for our task, for our desired motion. So after selecting a mechanism, that's the reason why we have to select the type of the mechanism. So appropriate link lengths must be determined in a process called dimensional synthesis. So after selecting a mechanism type, type of mechanism, appropriate link lengths must be determined in a process called dimensional synthesis. So this chapter focuses on dimensional synthesis. So this is important, dimensional synthesis. But let's say we said we have an input motion, input motion, motion, and there will be mechanism here somewhere. Let's say black box is go in and desired output motion. Output motion. So, output motion. So this is a question mark, huh? So, question mark. So input motion, okay. And we know which type of input motion we are going to apply. Mainly, it may be a rotation or translation. So it could be a translation like translation, linear motion, or could be a rotation. Let's say the counterclockwise or clockwise. So two types of motions. But the output motion could be very different. I mean, depends what we are going to do. Could be a motion like this, or like this, or any others. We will see later on, we will discuss the CAM mechanism, and in case of CAM mechanism, the output motion is very different regarding to 4-bar mechanism. So the desired output motion is the motion we use for the machine, for our task. So in order to create the output motion, desired output motion, or to produce the desired output motion, type of mechanism is important. Type of mechanism. So type is important. And then length of links. Of links. So has to be defined. And this is dimension analysis. Type definition. the type of mechanism, definition of type of mechanism, as well as dimensional analysis. Okay, let's start with the inline slider crank. You know that we already learned. Slider, inline slider. Inline means, so inline means, you know that inline. What means inline? Inline means these, let's say the A0 or A. Here is the B, and this is C. That means A and B is in the same line. Vertical, same line. So this is inline. So inline. And we know also the offset type, and we will talk later. So in case we need, so type is already we select the type, but why we select the type? So because we need output motion. Output motion like this must be given. So this length, stroke length must be given, like delta R phi here, maximum. This is given. So this is given. Okay, if we have to create such a linear motion, and okay, we first of all think, so which type of mechanism can, what we have actually normally as input motion, we have a rotary motion input, we have electric motor, isn't it? So the electric motor available everywhere, and since we have an electric motor, we have a rotary motion, so rotational motion. That means, so like this here, so rotation we have. So first, we have to think which type of mechanism can convert the rotary motion into the linear motion. That's we should know, first of all. And we know that the slider crank mechanism convert the rotary motion, rotational motion into the linear motion. So therefore, we select the linear, the slider crank mechanism. Why inline? So because we need only the linear motion, and we have another example with offset slider crank mechanism, and you will see it affects the output motion, and this type of output motion is different. So desired output motion here is the linear motion, but if we check the desired output motion as a graph, so let's use this color here. Let's say this is the output motion. We draw the output motion here, and in the vertical axis we have the input motion here. The input motion, let's say, it's turning in that direction, counterclockwise, and from 0 here, the angle, and let's say this is here is 0, and here we have 360 degrees for full rotation, and here we have 180, and here we have 90, and here 270. So, and we expect that the let's say this stroke start from the 0. Let's use the another color here. So the stroke will start from 0, and here will the maximum. Since it is in line, here will the maximum. Stroke will be maximum here. This is the maximum value of the stroke. So, and that means we think it goes like this and come back here. So if we measure the stroke starting from, let's say, from 0 here, from, we learned also the limiting position, isn't it? The limiting position was like this. Let's have here so this is here our A. The limiting position here. The limiting position is, since it is in line, so let's draw the line here. So the limiting position is somewhere here. One of them is here. And this is here the A. And let's say this is the rotation of A, is rotation like this. So this is here a B. One of the limiting position, this is B. And this is C here. So, and this length is here, you can easily imagine. This is length is here L2. We said L2. And this is L3. L3. This is one of the limiting position. The other one is, if we have this is, let's say, B here, B prime, let's say here, B prime, and then if we have B prime here, then this is L2, and we will have this here, the slider we will have here somewhere, and this must be here around somewhere. Here, let's imagine it is L3. So in this position, limiting position. So that's the reason in between the stroke will maximum. We measure the stroke, I mean, the distance from the 0, from here, this is the 0 value, and here, and back in that direction to the initial position. So this is like a triangle, but actually this is not triangle because the behavior is not linear. So it is like a curved, like this, and goes down here. So this is the maximum stroke length. This is here, half of the delta R4. Delta, sorry, no, not half. Delta R for max. Okay. So how can we design? That means we know the type. So type of the mechanism is, so type of the mechanism is inline slider crank. So inline is here Okay. Is in line slider crank. So inline slider crank is the type. But the dimensions we have to calculate, isn't it? So dimensions, that means, so we have to calculate the L2, L3, and L1. L1. That means, did say the, okay, L2, L3. If you know that L1 is not here, important because it's not constant, it's changing. So let's take it away. So, and maybe we have to calculate also the transmission angle here, the angle here. So how can we do that? So determine the L2 as also here written. So determine L2 and L3. So how can we do that? How can we determine L2 and L1? It's given is only, so you see the given is only for delta R for maximum. Okay. Let's continue. So in this picture here, you see we have the position, limiting position. We have here the limiting position. So the limiting positions. Limiting position. So the limiting position this is the zero line here, and this is the maximum stroke line showing the maximum stroke. So therefore, here you see this is L2 and this is L3 and this is here the maximum strokes we are going to achieve or to design a mechanism for that. So this is symmetrical slider motion. That means the motion is symmetric. It like this. I have shown the output motion will be like this. If we have here, let's say the 2P, that means 360 degrees, and here we have P. So, and then the curve will be like this. So here we have maximum, here we have maximums. And go back. That means slider will move from this position to this position, arrive the maximum distance, and then will come back. For for one full rotation of L2 or crank. And this is the stroke. Here the stroke. Delta R 4 value is millimeter. So so if we check this, so crank length, the distance actually here created in between here, the distance here in between created by the length of the L2 of the crank, this distance. So therefore, if we divide this delta R4 by 2, so we achieve the length of L2 like this. So L2. Now the problem is, so how can we define the L3? So L2 is easy to define. So delta R 4 max divided by 2 gives us the L2, because this is the difference between two limit positions created by the crank. That means length of crank L2. Okay. On the other hand, we know that to produce smooth acceleration, that means, see, the piston is moving between two limits here. That is a limit 1. Here the limit position L1, let's say limit 1 here, and this is the limit 2, maximum limit 2. Okay, here in between and the slider is moving in between the limit position. So this is linear motion, but this is not let's say the acceleration free. It has acceleration, it's not rectilinear, it's curvilinear. So therefore the motion along this line has an acceleration. That means the speed starts from the 0, and here is the maximum, and here stop. That means it starts from here with 0 and come here, and here the speed is maximum, and here goes down to the 0 and start again from the 0 into this direction, and here achieve in the middle maximum speed, and here has to stop. So therefore this curve, the slider undergoes this curve, this path, and this path is not rectilinear, so it's a curvilinear. Therefore it includes the acceleration. So acceleration is a headache and mechanism. Why? Because if we have acceleration, we have force of inertia. So force of inertia. And force of inertia are coming from acceleration. So of course, from the from the dynamic, our famous equations, let's write that here. F is equal F net m times acceleration. If we have acceleration, and considering the motion involved into this mass involved in this motion, so we have the moment of inertia, force of inertia coming from the acceleration. So on one side we can maybe reduce the mass as much as possible. But on the other side, we have to reduce also the acceleration as much as possible in order to have less or small mass moment of inertia. So mass force of inertia or force of inertia. So, and that's the reason why I say to produce a smooth acceleration, that means less acceleration. So L3 must be bigger than L2, not equal, bigger. So this is the rule of thumb. L3 maybe about equal 4 times L2 could be. But it depends also, do you have such time or not? I say pardon, sorry, place. Do you have such a place or not? If you say, okay, I select the, so I calculate, let's assume I calculate the L2, let's say the 2. Okay, then 4 times 2, 8. So that means L2 is equal to 2 millimeters or 20 millimeters. And then L3 is 4 times is equal, could be equal, okay. It comes from the experience, 4 times, so that means 80 millimeter. So then if you have 80 millimeter here, millimeters, and here millimeters, so that means here you have 100 millimeters, you have to have 100 millimeters. Okay, here is the 400 because 20 is 400, and from here 80. That means 120. So do we have such a place or not? This is also has to be also considered. So then let's continue. So according to this, you can select select L3. So there's no need to calculate it. And after selecting, you have to make analysis that you have to check whether the output motion is, let's say, the same as we considered at the beginning of the slide or not. Then you can play with the length of L3, considering this rule here. So let's have an example here. The exercise, that means design a slider crank mechanism with a stroke of 40 millimeters. That means this is 40 millimeter here, given 40 millimeters. So this stroke from between the limiting positions. 40 millimeter, the outward stroke must be consumed 0.2 seconds and return in 0.2 seconds. So you can imagine if we design such a mechanism, inline slider crank mechanism like this. So let's show the line here. And let's think this is our position of limiting position of the slider. One is the here, and the other one is here somewhere. And let's assume that in between we have 40 millimeters. So, and then, so if it is in between here somewhere, so let's draw the mechanism here. And this is our let's say let's assume this is our L2 length of crank and connect it here. So it is turning. So let's say the counterclockwise or clockwise depends. Let's assume that counterclockwise. So, so he's saying that the outward stroke must be consumed 0.2 seconds and return also 0.2 seconds. That means the slider, the crank is so move like this. This is making a circular motion like this. So needs from here to here, that's from here to here. It will take 0.2 second, and also from here to here, also 0.2 second. The time is very important. Time is very important. Why time is important? Because the machines we design has to be calculated. I mean, this is the cycle time, because the product produced in this machine evaluate by the cycle time. So what is the cycle time here for a full rotation? 0.4 seconds, isn't it? 0.4 seconds. That means we know the actual angular velocity. Angular velocity is, if it is constant, I mean the rotations constant, is to rotate with constant speed. So you know, W is equal d theta over d t. That means delta theta over delta t, and here is this. Sometimes we have so in this case it is symmetric. I mean, that means the forward stroke and return stroke will take 0.4 seconds. So we can easily calculate the omega value. This is here the 2p over, for full rotation, over 0.4. So radian per second. So that means we can also select a electric motor accordingly with gear, for example. So we know actually the angular speed. We can calculate the angular velocity here. Later on, we will talk about, we can calculate also the tangential speed is also possible. Huh? So, but we will not involve in issue of speed, velocity. We know from this exercise that 180 degrees will used for the advanced stroke, and 180 degrees will use for the return stroke. So there is no so there is a symmetry between the advanced stroke and return stroke, but it is not always like this. And sometimes we have, for example, we want that the advanced stroke must be slower than the return stroke, or return stroke must be faster than advanced stroke, because in in advanced stroke, if let's say this goes in that direction, this is the advanced stroke. Let's think that is the limit position 1 and the limit position 2. So if it goes from this position, from the limit position 1, initial position, let's say, to the advanced position, so in most of cases we need a slow motion, because the piston maybe is doing a work, and this work needs a certain speed, not fast, slow. But if the mechanism do the work in advanced stroke, then maybe the advanced stroke must be slower than the return stroke, because return stroke we have to take it as quick as possible to return, so that we start the second cycle. So that means the cycle time, it affects the cycle time. So therefore the advanced angle, that means the angle considered for the advanced stroke and the angle considered for the return stroke, is also important to design the machine, to design the mechanism. So here the solution of the first one, crank length, we can we can say we can take the crank length. We calculate the crank length, the half of the let's say the stroke, and this is the let's say 200 to say 20 millimeters, and then the L3 can be calculated depending. I mean, the L3 depends on the place we have. We can say L3 is equal at least 4 times L2. L2, and if we don't have place, we can reduce. So by considering the place, because if we establish such a mechanism, so the place is also important here, from here to here. So where we are going to install the mechanism. So we have to consider also this length, and this length comes from the machine, from the environment of the machine. So if we have enough place, so we can keep this rule that we can say L3 is equal 4 times L2. But if not, we shouldn't. We should consider the place we have. And we have to take, and if it is not like this, so we have taken the risk the acceleration. Okay. So let's make 10-minute breaks, and we will start at 2 o'clock, exact sharp at 2. Okay, we can start. I hope you can hear me.
Yes, I hear.
Okay, thank you. So thank you for feedback. Okay. So let's have a quick overview to the first exercise here. Inline slider crank. Inline slider crank, we said that the advanced stroke, that means the advanced stroke that the motion start from here. This is the pencil here. Motion, let's say, start from here and goes to this point. This is the half of the rotary motion. That means 180 degrees, and it takes 0.2 seconds. And the other part, let's say from 180 to 360, is also 0.2 second. That means we use the half of the way for the advanced stroke. I mean, the half of the angle, rotational angle for the advanced stroke, and half of them used for the return stroke. Let's say this is the advanced stroke here. This is the advanced stroke, and this is the return stroke. So the return stroke, return and advance. So now it's okay, but and we know that this is a inline type of crank slider, slider crank mechanism, inline. So if we have inline mechanism, so we think that we will have the half of the rotation for the advanced stroke, half of the rotation, that means the input motion of input, or the input motion, half of the input motion for the advanced stroke, half of the input motion for the return stroke. But we said also the other type of expectation regarding this issue. So here it is saying that the offset slider crank mechanism and 4-bar mechanism produce quick return actions. Quick return actions. So we have here, and we can also by using this offset slider crank mechanism and the. And by the way, this is a mistake. I have to. Okay. Now it's okay. So, so offset, both of them, huh? The offset slider crank and 4-bar mechanism produced quick return actions. So that means quick return action is possible. Is not possible for inline crank slider, but it is possible with the offset slider crank. So what means quick return? So let's talk a little bit about what means quick return here. So the quick return. That means we have a rotation input motion. Let's say the input motion is our input motion, mostly a rotational motion. Input motion comes from the electric motor. Input motion, but sometimes we have also linear motion, could be, but mostly we use the rotary motion. Okay. So the input motion is a rotary motion like this. We have a rotary motion start from here and come from this to this point. So, and this is 360 degrees for full rotation. But in the output motion, we sometimes expect that the quick return. So quick return means we spent less angle for the quick return than the angle for advanced stroke. Or the forward motion. So here the time ratio is defined by Q. So here is the mistake. I have to time ratio we can indicate with Q. So the Q is time. So how can we define the Q? Q is defined time of the advanced stroke, time of the return stroke. That means time of slower stroke, time of quick stroke. So if our advanced stroke and return stroke. So advanced stroke or advanced motion or return motion. So quick return, advanced motion or return motion. So this is also another as said expression. So the advance motion and the other one is the return motion. So and it must be maximum equals 0 or less than 0. Why is it so? So let's think about. So if it is equal 1, that means the advanced stroke and return stroke is equal. That means we divide the input motion into parts. So 100 degree advance, 180 degrees for advance, 180 degrees for return. But if it is less than 1, if it is bigger than 1, as here, if it is bigger than 1, that means the advanced stroke take more time. Since we use the constant speed, angular speed, that means the angle getting bigger than the return stroke. Return stroke take let's say the small portion of the angle of rotation. So then we define the imbalance angle beta, like this here. So what is imbalance angle? So imbalance angle is if the return stroke and the advanced stroke, if you don't, let's say, use the same angle for rotational angle for advanced stroke and return stroke, that means there's a difference in between, and this difference is the imbalance angle. So you will see now here. So an imbalance angle beta is a property that relates the geometry of a specific linkage to the timing of the stroke. So this angle can be related to the time ratio Q. So then we know from the first equation, we said the Q is equal time of slower stroke over time of quicker stroke, and must be bigger or equal to the 1. And we can write, actually, if it is not equal 1, that means, so if it is, if we say, if we would say, so in abbreviation here, time of slower stroke over time of quick stroke is equal 1 in, let's say, in limits in situation. So that means time of slow stroke is equal, isn't it? Time of slow stroke is equal time of quick stroke. That means the input motion is divided into parts, angle-wise. But if it is bigger than 1, so that means time of slower stroke take more portion of the rotation angle than time of quicker stroke. So that means we have here on this part we have 180 degrees plus beta. Beta is the imbalance angle, and here we have, since we will have in total 300 in total, we should have 360 degrees, and here we have in this part 180 degrees minus beta. Or we can write, so if we let's say solve the beta from these equations, and then we can calculate the beta like this. So beta is equal 180 degrees in bracket Q1 Q minus 1 over Q plus 1. So what means that for us? So let's have an example here. So the example is following. A quick return mechanisms is to be designed where the outward stroke consume 1.1 second and the inward stroke consumed 0.8 second. So outward and inward. That means advance, and so this is the, so we are going to design a quick return mechanism. This is the so quick return mechanism, and the design, and where the outward stroke consumed 1.1 second and the inward stroke consumed 0.8 second. Okay, determine the time ratio. So in this time ratio, imbalance angle, and the space at which the mechanism must be operated. Speed at which the mechanism must operate. Okay, so let's first of all the time ratio. What is the time ratio? So how can we calculate the time ratio? First of all, we have to calculate the beta. So we know the Q. Q is the where is it? Here Q is, so Q is the outward stroke return must be quick, 1.1, and inward must be in what? 0.8. 0.8. So time of slower stroke, time of quicker stroke. Okay. So then this is equal. Let's calculate that. So 1.1 over 0.8 is equal. So this is 1375. So 1375 and is equal 1375. So we know the value of Q. So we can calculate the imbalance angle now. So the time ratio, this is the time ratio. The imbalance angle is, you see here, imbalance angle is beta. Beta is equal 180 degrees, 180 degrees in bracket, Q minus, okay, Q minus 1 over Q plus 1. Q plus 1. So, so then beta is equal 180 times we have here minus 1 is 0.375 over plus 2.375 because 1 plus, huh? So, and what is the result? Let's calculate the result. Here, and times 180. So this is around 2842. So this is the angle, imbalance angle. So this is imbalance angle. Okay, the next one is the speed at which the mechanism must operate. Speed, that means the input speed. The input speed. So how can we calculate the input speed? Input speed. We know the total time actually. Total angle and total time. We know that. Total angle is for a full rotation is 360 degrees. 360 degrees. And this radian wise is 2p. 2p. So, and the omega is equal delta, omega is equal delta theta over delta time used for this angle, delta t. And here in this case it is 2p, because we are calculating as radian per second, 2p over what? Over time. And the time is how much? 1.9 second. So this is 1.9 second. Because we have to take inward time for outward stroke and time for inward stroke. So the total time used for these 2p. So then let's calculate the angle 2p over 2 pi over 1.9. So is it pi times 2 is equal over 1.9 is equal. So 3.3 radian per second. Here, let's say. So then this is equal 3.3 radian per second. So this is the input speed of our mechanism. That means we have somewhere, if we have a slider crank mechanism, inline offset must be offset, because inline we cannot create different time used for outward stroke and inward stroke. For different outward and inward stroke or inward stroke, we have to use offset slider crank mechanism like this. Offset means like this. So the slider is somewhere here on this line here. So, and this is our length 2, and this is the length 3. So there is a distance here in between. This means offset slider crank mechanism here. Let's say this is L1. This is L2 here, and this is L3. So we have to define. So what should be L3, what should be L1, and what must be L3. Sorry, L2 here, L1. I made a mistake. I have to go to L2. This is the 2. L1, L2, and L3. So, and then we have to be sure that the outward stroke will take 1.1 second and inward stroke will take 0.8 seconds. So that means the angles will be different. So return angle for the return stroke, the angle must be, so advanced stroke, the angle must be 180 plus 80 plus beta for outwards, let's say the for outward stroke, outward stroke, so use more angle. That means the more angle for outward stroke. That's the reason why it takes 1.1 second. And for inward stroke will take 180 minus beta. And this is for inward stroke. Okay. So so actually, if we have say the different different speed for inward and outward stroke, that means different time. We use different time for inward and outward stroke. So how can we calculate the imbalance angle? And after that, what is first of all, what's the time ratio? And the time ratio, and how can we calculate the imbalance angle, and the speed of which the mechanism must be operated? How can we calculate? So all those things I calculated already. Now we have to calculate also the length of L1, L2, and L3. Then we are able to design a mechanism for, let's say, the inline or offset crank slider mechanism for a given output motion, or for a desired output motion. So here, let's talk a little bit about the offset slider crank mechanism. You see the main difference between inline and offset slider crank mechanisms is this length here. You see this length here, L1. If L1 is 0, then it is inline. If there is L1 is not 0, it is offset. So recall that an offset slider crank has quick return actions. So we know that from experiment and from experience and so on. Because, we use more angle for advanced stroke, rotational angle from the input side, and we use less angle for the return stroke. And that's the reason. It comes very quick back, and it goes slowly forwards. So, but must determine the required Q angle and the imbalance angle. So to time ratio and imbalance angle. So the task is to determine the appropriate L1, L2, and L3 to achieve the required stroke and the balance angle. So the time ratio is given, must be given. So the time ratio must be given, Q must be given. So Q is given as time ratio, as time ratio, because you have to know that. That means the outward and inward stroke time-wise, how many seconds takes the outward, how many seconds takes inward stroke. And then we can calculate the beta imbalance angle. So beta And then we have to also the stroke must be given. Delta R max, delta R4 max, also given. So then we have to calculate what is the L1 and L2 and L3. So has to be found. Okay. 1 second, please. So let's talk about the solution. So how can we find L1 and L2? So again, offset slider crank mechanism. Since we have outward and inward stroke, it take inward and outward different time, consume different time. So again, we need we need also the information about the space where we are going, the machine or the space where we are going to apply the mechanism, where we are going to use the mechanism. So how much space we have. So this is initial arbitrary set. So here, this is the line here, this is the and L2, and we now, we can calculate the L1, but first of all, the L2, you see here, this length is here L3 and L2 in this limiting position, and in this limiting position we have L3 minus L2. L3 minus L2. So, and this is L2 minus L3 here, and this is here delta R max, it's already given, and this is the angle, imbalance angle you see here. So using these geometrical situations, what can we do? We can do following. So we can draw a line like this and show the maximum stroke, and we can do following. So defining the beta we know already. We know that this is the beta. So using the angle, we can define this point here. So the angle, we can, let's say we can, first of all, the point A, we can indicate the point A here somewhere. This is the column A. Let's assume that the C1 is here, C1. And draw any line like this here. So any line goes through. And then we know the beta, and using the beta angle from somewhere, and we can draw another line. And this is, we know this angle here because we can calculate the imbalance angle. So we know also this point. If we have the C1 and C2, that means delta R max is given. We know C1 and C2. We can select, let's say, the free C1 and C2, and then we can draw any line from here, and any line from here, so that the angle in between must be beta. So where these two lines are crossed to each other here, so then that means this is the point A. Point A. So if you know the point A, and let's say point A, and draw this line here, this is the one of the limiting position, and the other one is the other limiting position. So this is the R2, so this is L2. We can easily find it, L2. So since we know the L2, and we can select L4 according to this rule here, and L1 is already we can get from the drawing. So using a computer-aided design program like SolidWorks or CAD program and so on, we can easily calculate the length L1, L2, and L3 using these geometric relations. Okay. On the other side, we have such a curves prepared for the designer. And in this curve, you see here the relation between, that means L1 over L2. L1 over L2 is 0. It starts from 0. And or 0.2 or 0.5 or 1.0. So 1.0 means 1 to 1. Huh? That means L1 is equal L2. L1 is equal L2. Huh? So, and then we can also so we already talked that we can first calculate the L3 over L2, and if you know that, and if we know which one we are going to use, which of them, because it's a let's say the selection, but considering the maximal normalized slider acceleration. So this is the one of the important point we have to consider, maximal normalized acceleration, because we don't like high acceleration. Acceleration means especially for the slider here. So the acceleration, because slider has a certain mass, acceleration, high acceleration means, we already talked about, high acceleration means F, force of inertia. F is equal ma from this equation, second law of Newton's. If we have high acceleration, that means we have high unbalance force. And high unbalance force causes vibration and fatigue and vibration and noisy and all those things. We don't like actually. We are interested to reduce as much as possible. To reduce it as much as possible. That means the acceleration. So if we design a 4-bar mechanism, let's assume inline slider crank or offset slider crank or general 4-bar mechanism. So you have to consider that you will have acceleration during the motion, and acceleration means unbalanced force. It is not easy to balance. So, and the in design period or design stage, you have to consider take into the consideration, how can I reduce the acceleration? So how can I have a smooth motion, let's say with less acceleration? Because high acceleration means high unbalanced force. Okay, so the offset mechanisms, how can we the solution here discussed once more. Solution you see here. So this is what we have to, the first, what should we do? In order to solve this problem, to calculate L1, L2, and L3. So first, locate the axis of the pin joint on the sliding link. Okay, this axis here. Huh? So this one, this sliding axis. Okay, this joint is labeled as point C in figure A. Okay, C is here somewhere. And then secondly, draw the extreme positions of the sliding link. Extreme position, that means C1 and C2. Separated by the stroke delta R4 max, which is given here. Okay, this is second step. And the third, at one of the extreme position, construct any line M. This is the line M here. Where is it? Here you see the line M. From here, from C, construct any line M through the sliding link pin joint inclined at any angle, like this here, and then theta angle theta m. Okay, theta m. These points is labeled as C1 here. This is theta m here. Must be theta m here. So this angle here. This you can select it. Huh? So, and the fourth, at the other extreme position, this is the C2. Extreme position, draw the line N. Line N is this one here. You see the line N here with the angle theta n. But we have to be sure that the angle in between must be beta, the imbalance angle. And the sliding link pinpoint, a pin joint labeled C2 and inclined at an angle beta from the line M. Note that theta n is equal to theta m minus beta. So this must be theta. This is actually theta m, theta n. I made it, so I have to correct it. Theta okay. Theta. Let's correct it, huh? So theta m here. Theta, where is theta? So, okay, now it's correct. So, okay, theta m. And theta m, is it theta n? Okay, this is correct now. Oh. Okay. Now we can continue. So then theta n, you see here the theta n is equal theta m minus beta because of the triangle relation. You know that from the mathematics. So then continue with the intersection of the line M and N. This is this point here. Huh? Intersection of the line N and M defines the pivot point for the crank, point A. So this is the point A here. It's here. So the offset distance L1 can be selected from the construction figure B, you see here, can be selected. Since actually this is already selected because we defined the point, we defined the line here, this line, and in this line we defined the C1 and C2. This is a horizontal line, and the distance is also given as delta R for max, and then L1 is already defined. So then from the construction of the limiting position, it is observed that the length between C1 and D is 2L here between C1 and A, C1 and D, where is D? Here is 2L, okay. Note that this arc C2D is centered at point A because both lines are radii of the same arc. The radius AC2 is equal to the sorry, is also mistake here, to the length AC1 plus C1D. The rearranging this relationship gives the substituting gives these equations here, and then substituting and arranging the lengths of the crank L2 for this offset slider crank mechanism can be determined as L2 is equal 1 over 2, it's half of AC2 minus AC1. So then L2 is already, L1 is already, we know, L2 is also calculated. Then the 7, so AC1 is equal to L3 minus L2 from this construction of the limiting position, it is also observed that AC1 is equal to L3 minus L2. Rearranging the lengths of the couple, L3 is L3 for this offset slider crank mechanism is like this here, can be calculated. So the complete mechanism is shown in C here. You see that the complete mechanism here. The design procedure implemented with a CAD, computer-aided design, or AutoCAD or Solid or any other design software achieves accurate results. Note that any line M can be driven through the point C1, like this here. This is it was the C1 here. You see, any line M can be at any arbitrary inclination angle theta m here, like this here, theta m. This one is theta m. So therefore, an infinite number of suitable mechanism can be designed. In general, the mechanism that produce the longest connections arm have lower acceleration. We already discussed. The coupler must be as long as possible, and also consider the space we have in the machine. We have to install into the machine. So, and subsequently lower inertial force. So, force of inertia. Okay. So the offset crank mechanism, offset slider crank mechanism, you can also calculate the L1, L2, and L3 analytically. So there is the analytical method can be incorporated by viewing the triangle in figure B, like here. Generate expression for the link lengths L1, L2, and L3 as function of the stroke maximum, the imbalance angle like this, inclination of the arbitrary line M and theta M. So using these equations also you can calculate analytically. The first one, we learned how can the graphically we can calculate the L1, L2, and L3. Now you can also calculate analytically L1, L1, L2, and 3, and we can design the mechanism. So there's an example here. Design a slider crank mechanism with a stroke of 50 millimeters. The outward stroke must be consumed 0.35 seconds and the return 0.4 seconds. So this is the homework we will do. So I know that I couldn't send the homework to you, but I will add also this example to the homeworks I prepared for you, and you will get it via the Orlean platform. Please check it today, at least tomorrow. Check and start to do the homework, okay? So we finish for today. Then next week we will discuss how can we design a 4-bar mechanism and for which type of application we can design a 4-bar mechanism. So we will continue next week. Okay. Any question?
Hojam, this homework is on Olearn. Did you upload it?
1 second. So now I'm hearing now.
This homework, did you upload it on Olearn?
Not yet. I will upload it. So today, but you should check it tomorrow at least, huh?
Okay, Hojam. When do we have to submit this?
Maybe 2 or 3 weeks before midterm.
Okay,
You have to finish it. Okay?
Thank you.
So you are welcome. So have a nice week. Bye.
Bye.
Hocam bir soru sorabilir miyim? Çok kısa. Bu dersler
Okay.
alakalı değil ki de dün Machine Design dersine gelemediğim için dün soracaktım aslında. Şimdi sistemden ben ödevi yaptım ama şeyi check edemediğimiz için ödevi gönderdikten sonra doğru ve yanlışlarımızı görebiliyoruz. Diğeri gibi ikinci sınavı da açmadı.
Onları düzelttik. Şimdi yeniden yapabilirsin onları. Orada eksikler vardı geçen dönem olduğu gibi.
Anladım.
Şimdi düzelttik. Tekrar yaparsan göreceksin, düzelmiştir o.
Şimdi bir daha bakayım ben o zaman hocam. Olmadı yine sizinle iletişime geçerim. Teşekkür ediyorum hocam.
Tamam.
Diğer derste görüşürüz.
Tamam, oldu.
İyi günler, görüşmek üzere.
İyi günler. Sağ ol.